Graphs and networks, flow problems, minimum cut, and maximum flow. So connector problems in graphs and networks are looking at the maximum amount in a weighted directed graph that can flow through. So if you think about, in this example down here, I've got a source where everything's coming from and a sink where everything's going from to. If I've got say 8 liters or 8 cars per hour or whatever it is, 8 liters per minute going from source to A, but only 3 liters a minute can flow from from A to T, then only 3 liters is going to get through here per minute, even though 8's coming into the system from here. So the capacities of our weighted flow diagram graphs are important for working out the total amount of stuff that can be moved. Fascinatingly, there's a really interesting report from World War II, I think, era Germany about the maximum amount of equipment, people, weaponry, etc., that could be moved on the train network. And it's really a fascinating precursor to all these flow problems. I'll link it somewhere on Daranet. Anyway, so our options for finding maximum flow are often about cuts in the graph. Now, the maximum flow is obviously the maximum amount of stuff that can flow through the system. It's often hard to work out just by inspecting, so there's a method where we search for cuts. A cut is literally cutting through the network, separating the source from the sink. So source is where everything's coming from, sink is where everything's going from. Two, they can't both be S, so its source is S, sink is T. So a cut, say going through here, completely separates the source from the sink. A cut going through here, you can still get flow through. It's not an acceptable cut for our plan here. Now, cut capacity is the sum of the capacities of the edges or arcs that are cut. There's a little bit more to it than that. And the little bit extra is that only arcs or edges that flow from the source side to the sink side are counted. So we'll show you what that means when we get to our example. And the minimum cut, smallest cut capacity, is equal to the maximum flow that can go through the system. Whoops. Minimum cut equals maximum flow. Now, we will work through the one example, and I'll do it twice. The reason I'll do it twice is that sometimes you're going to find this easier to do by inspection, just looking for the maximum flow logically. So let's get a different colored pen. How I tend to do this by inspection is I'll look at what is coming into the system. I've got 19 coming into the system from the source. I'll look at what's the most that can be coming into the sink. 3 plus 5 plus 1. Okay, the most that could possibly be coming into the sink is 9 because that's all that's here. So there's definitely something reducing the maximum flow from here. So what I tend to do is track backwards and see what's getting through. So here from C to T, there's only one coming through. Do I have enough to feed into that? Yeah, I've got 11 that could come in. So that one can definitely get through. Then I've got this possible 5. Can I get all 5 going in? Now I can't, because while this 11 is coming in, there's only 3 coming up there. So that's blocking anything more from coming in through that 5. So actually I can only get this 3. Now, there's no real convention for how to do this. You might like to say, well, look, I've got 3 coming through here and through here. So I've got 3 actual flow coming in there. Then, now the kind of rule you think about with water, if water can go somewhere, it will. Annoyingly, that's why there's leaks in my house. So even though 5 could go up there, there's nowhere for that to go. So you don't have to allocate any of this 3 that can come through to go up to here. It can all go there. Then this 3, I've got 8 coming here. 3 of it can get through there. So what I have is I can get 3 plus 3 plus 1 coming through. Now they haven't told me if this is people per hour or liters per minute or whatever it is, so I'm just going to leave that as 7. If they'd told me what it was, I would say 7 liters per minute. Now that was just inspecting and logically working through. I'll come back to this actually. If we did the minimum cut method, then we'd look for where we can cut the source to the sink and find the minimum. Minimum cut gives us maximum flow. And you literally draw cuts. So I could cut through here. That's C1, and C1 goes through 3, 5, 1. 3 plus 5 plus 1 equals 9. And we're just looking for the capacity of all the possible cuts. Now it's easiest to, I work from the top and I work out, okay, so here I've gone through AT, BT, CT. Can I now go through AT, BT, and somewhere else? Yes, I can go over here. So I'm trying to be quite methodical about making sure I've got all the cuts. So that goes through 3, 5, 3, 11. So quite a lot there. What have I got? 8, 9, 10, 11, 22, I think. C3. All right, so I've gone through AT, and I've gone through this one and this one. So that's everything I can do coming through AT and BT, but I can come through here now. So that's C3. You see, it's slow, it's time consuming, and it's hard to work out if you've got all the cuts. That's 3 plus. Now, this doesn't get counted because it's going back from sink towards source. So this is 3 plus 3 plus 1. That's 7, and we know from our previous example that that's our maximum flow. If you look back at this example, you'll see that's where I've circled that this was all that could get through. Nothing could get through here, but it's going backwards. It wasn't helping us at all because this is blocking. That, going through the 3 that I circled, gives us our minimum cut, which gives us our maximum flow. So actually, if I had the time in a test, I would do a problem like this both ways. I'd inspect it and try to work out where my limitations were, and then I would expect my minimum cut to come out to that and go through where my limitations were. So that's C3. Now I've come through here, here, and I went back. So now I can come through here, here, here. And that's going to be C4. And that's 3 plus 11 because we don't count that 5 because it's going back. It's no help to us if it's going backwards. So that seems to be everything that I can do coming through here because I can't go here, here, here because that's not a full cut through the source to the sink. So that's everything I could do coming from the top through that one. Now I've got to come through the top through that one. This is tedious, I know. Come through here. All right, I can go through there and down. C5, 8. Don't count the 5 because it goes back. 5 and 1. C6. I can go through here. So I've gone through there. Only when I was don't go backing, looping back on ourselves. That's not helpful at all. So this is 8 plus 3 plus 1, 12. And of course, we can go straight through here. C7, 8 plus 11 is 19. So it's time consuming, it's annoying. This is a lot faster. If you're in a test and you're out of time, do it this way if you feel comfortable with it, and then come back and check with your cuts if you need to. But you do need to be able to show what the capacity of a cut is. You do need to show that the minimum cut is maximum flow, so we better finish our question here. Therefore, maximum flow equals 3 plus 3 plus 1 equals 7, because that's our minimum cut. And you do need to be able to remember that a cut has to completely separate source from sink. You do need to remember that you don't count arcs or edges that are going backwards in your capacity of a cut.